In our last learning module, we learned about the integral test. If we wanted to understand whether a certain series converged, if it was a positive series and decreasing, we could compare it to an integral. But there are certain series that are pretty darn hard to do with integrals. How are you ever going to integrate that? You'd have to find the integral of 1 over x squared plus natural log of x plus 7. That's fairly hopeless. Or how about that? The integral test only applied when the function was decreasing, and this is not decreasing. It actually wiggles up and down. It decreases in the long run, but it wiggles up and down on the way. So the integral test doesn't even apply. So how are we ever going to figure out whether series like these converge? And the answer is that we're going to compare them to the series, the sum of 1 over n squared and the series of sum of 1 over n. Now, to do these comparisons, we need to know what kind of series are more likely to converge than others. And we're going to pay attention to positive series. We're going to assume that all of the terms in our series are non-negative. It doesn't actually have to be positive. Non-negative is good enough. And for those series, the partial sums grow monotonically because each term adds to the partial sum. Sn is an plus Sn minus 1, so it's bigger than Sn minus 1. Since this is a monotonic sequence, it converges if and only if it's bounded. So the series converges if the sequence of partial sums converges, and that converges if the partial sums are bounded, and each of these are if and only if. So either the series converges or the partial sums go to infinity. If the partial sums go to infinity, it diverges. If the partial sums don't go to infinity, it converges. So our idea of the comparison test is we're going to compare the sequence an, which we're given, to some other sequence bn that we already understand. And if bn converges and a is somehow better than bn, then an is going to converge. And if bn diverges, and a is somehow worse than bn, then the sum of the an's has got to diverge. So what does better mean? Well, bigger isn't better. Smaller is better, bigger is worse. So here's the theorem. The theorem says, suppose that the sum of the an's and the sum of the bn's are both non-negative series. All of the an's are non-negative, all of the bn's are non-negative. If all of the an's are less than the corresponding bn's, and the bn's converge, then the sum of the an's converge. In other words, if bn is good, it converges, and an is better, it's less than bn, then an is good. If the bn's diverge and the an's are bigger than the bn's, so in other words, if the bn's are bad and the an's are worse because they're bigger, then the an's diverge. So let's see how that works for our examples. So for our first example, we were looking at the sum of 1 over n squared plus log n plus 7. Well, I claim that that's less than 1 over n squared because n squared plus log n plus 7 is bigger than n squared, so 1 over n squared plus log n plus 7 has got to be less than 1 over n squared. On the other hand, the sum of 1 over n squared converges. That's a p-series with p equals 2. P-series converges whenever p is bigger than 1. Since this converges and this is less than it, this messy guy also has to converge. On the other hand, if you look at log n plus sine squared n over n, well, that's kind of a mess, but once n is 3 or bigger, log n is 1 or bigger, sine squared n is 0 or bigger, the numerator is bigger than 1, so we've got something that's bigger than 1 over n. But the sum of 1 over n diverges. So this messy thing has also got to diverge. It's bigger than something that diverges, so it diverges. So why is smaller better? Well, let's suppose that the ANs are smaller than the BNs, and everything here is non-negative. And let's let Sn be the partial sums of the of the a's, and we'll let Tn be the partial sum of the b's. Since each of the a's is smaller than the corresponding b, that means that Sn has to be smaller or equal to Tn. Now, we assume that Bn converges. If Bn converges, then the sequence of Tn's converges, so the Tn's are bounded. But that means that the Sn's are bounded, because any number that's bigger than all of the Tn's has also got to be bigger than all of the Sn's, which are smaller than the Tn's. And since the Sn's are bounded, the Sn's converge. And that means that the sum of the AN's converge. On the other hand, if the AN's are bigger than the BN's and the BN's diverge, well then the partial sums go the other way around. The partial sums of the AN's are bigger than the partial sums of the BN's. So if BN diverges, the TN's have to diverge, which means the TN's are unbounded. They get bigger than any number you can name. But the SN's are bigger than the TN's, so the SN's are unbounded. If the SN's are unbounded, the SN's can't converge, and AN diverges.